Welcome to this edition of the Henstitute. In this one, we're going to talk about a thing called a Venturi tube. And a Venturi tube is basically one in which the tube is stuck in the water and you can blow air or force a stream of air through the horizontal tube. So the air is going to be moving through here, and the other end is actually sticking in the water. So the idea is we're trying to figure out how much the water is going to rise in this tube, because it's going to rise in this tube. If air is forced through the horizontal tube at 7 meters per second, how high will the water rise in the vertical tube above the level of the water in the container? So what we're trying to do is figure out what this height right there is going to be. With this situation, a couple of things that usually happen is, again, if we're going to use Bernoulli's equation, we need to make sure we have picked, whoops, this should not be a 1/2. We're going to pick what exactly we have in terms of point number 1 and point number 2. And that's going to be important. Now, the nice thing is it doesn't actually matter what you pick. My suggestion is I usually try to go with something that deals with height. And here's what I mean by that. When we did fluid statics, anything that was higher up in the fluid was number 1, anything lower in the fluid was number 2. So for this particular situation, I would probably pick this right here is number 1 because it's higher up, and this situation is number 2. And that's probably the hardest part, is figuring out those two different situations. This up here, number 1, we do have the fluid moving across there, but it's air that's actually moving across there. So that's one of the things that's kind of weird about this. You're like, wait a second. We have air flowing across the top. What do we actually mean by that? What exactly is going on as that's actually happening? And the second part is you go, okay, what is happening with our different parts here? So for example, we have the water. Do we need to use the density of the water? That's what we're dealing with. Or are we dealing with the air? And those are things that are going to be a little more difficult. So we'll go into those. The first part is, let's look at speeds. So with pressure number 1, we don't know what this pressure number 1 is because we have the pressure above this fluid. We're trying to figure out what that is. I know with a faster moving fluid here that it's got to be lower pressure. So I'm going to leave that as a question mark for right now. For V1, what we're actually going to be looking at is the fact that the air is forced over there at 7 meters per second. So that's going to be my V1 as we kind of do this. And then H1 is what we're actually going to try to find, how high up this is actually rising in this fluid. The next part is our P2. So P2 here is going to be air pressure. So we should be able to solve that. And then V2, this one's kind of a confusing one. People always go, well, how fast is it going there? What is the V2? And so I'm going to say that the V2, the air above here is basically not moving at all. So you have it almost equaling 0. So we're going to actually cancel out that part. The other one is, since we're trying to figure out the height that it rises above this level, we can actually make this be our origin. So this can be a height of 0. And so when we get up here, this is going to be our H1 because it's going to be the height above that. So our H2 can become 0. And so we can actually cancel out that one as well, which is kind of nice. So as we get ready to kind of solve this, this is what we're going to go after, is how do we go about actually dealing with these different quantities. So here's the really cool part with this one, and it's also the confusing part. We actually have to do this equation twice because right now I don't know what the pressure above the water is. And interestingly enough, this V1 is not this. It's not the 7 meters per second. That's how fast the air is moving. But if I'm doing water here, then I need to actually use the velocity of the water, but the velocity of the water at 1 is 0. So this part disappears. And then you're like, wait a second, how do I solve this? I've got P2, which is air pressure, but I don't know what P1 is. That's going to be the pressure of the air above that tube. So now we actually can do this by coming back and using the 7, where this is going to be the velocity. So let's take a little break and let's go and let's look at what's happening in the air up here at the tube. So our 2 points here, I'm going to actually call them A and B just for a difference, is we're going to look at the air outside of the tube. I'll call it A, where the air is basically not moving. So the velocity at A is going to basically be 0. And we're going to have A be basically at the same level of the tube. And then the other point we're going to look at is inside the tube. I'll call this B. And B, we do know how fast it's moving. It's moving at 7 meters per second. But then we also have no difference in height. So HA can be 0 and HB can be 0. A is going to be the pressure outside the tube. The pressure outside the tube is just plain air pressure. So that'll work. And then the pressure inside the tube is what we'll deal with. So I'm going to have another little equation I'm going to write over here. And it starts out looking exactly the same as this one, except that I've narrowed it down. So I have the pressure outside the tube, PA. This is going to be air pressure. I'll write that as air. Plus my 1/2 rho V1 squared or VA squared has canceled, it's 0. And my rho GHA is also going to be 0. So I don't actually have any kind of plus to that side. So outside of the tube, we don't have anything. Inside the tube, PB is what I want. And PB is going to be the same thing as P1 here. This is going to be the pressure above that air. This one does not have a rho GH because HB is 0, but it does have a 1/2 rho times VB squared. So what this shows us is when you have air that's actually moving, the reason why you have lower pressure is because you could have air pressure outside, and then this pressure here has this little extra component. Well, it doesn't actually say it in the problem, but it does say that it's air that's forced over the top, and I should have probably written on here, but the density of air is actually 1.29 kilograms per cubic meter for its density, just like the water we know is 1,000 kilograms per cubic meter. So since we didn't actually know that number, I have to give it to you, so I'm just giving it to you now. So we can put our numbers in. Same with our pressure of the air. We know this is 101,300. PB is what we're trying to find, plus the 1/2. This is 1.29 times my 7 squared. So I pull out my handy dandy calculator. I take the 1/2 times 1.29 times 7 squared. So this little component over here is 31.6. 605 to be exact, pascals. So I'm going to subtract that from the other side to find PB. So PB is going to be 101,300 minus this value. I'm not going to round anything right now. I'm going to go ahead and leave it as 101,268.395 pascals. The reason why is this is so small, it doesn't seem like it does very much, but it does actually decrease the pressure. So I need to make sure I have that. So now I can put that over here as P1. So I have this value. So I'm going to switch this back to red. So this is my 101,268.395. This part was 0 because the water is not moving above, but I do have this part. This row is different, so this is the 1,000. This is 9.8, and then H1 is what I'm trying to find. Over here, I've got P2. P2 is air pressure, 101,300, and then we don't have anything else. And so I'm going to try to find what H1 is. Here's what I want to kind of show. When I take this and I bring it over to the other side, what I end up with is 9.8 times 1,000 is 9,800 times H1. And guess what? That is just going to be my 31.605. In other words, it's the difference in pressure due to the moving air. So this is just the 31.605 again. I can divide that to find H1. So I take the 31.605 divided by 9,800, and I get 0.003225. That's in meters. So basically about 3 millimeters. So it's not rising very much when you're only blowing at 7 meters per second, but it does do it a little bit, I suppose. This really only has 1 sig fig, so I should just say this is 0.003 meters or 3 millimeters. So that has been a slightly different version of the Henstitute video on fluid dynamics, but still applications of Bernoulli's principle. Hope you enjoyed.